Section 1.4, Composition of Functions. Learning Objectives. In this section, you will 1. Combine functions using algebraic operations. 2. Create a new function by composition of functions. 3. Evaluate composite functions. 4. Find the domain of a composite function. 5. Decompose a composite function into its component functions. Suppose we want to calculate how much it costs to heat a house on a particular day of the year. The cost to heat a house will depend on the average daily temperature, and in turn, the average daily temperature depends on the particular day of the year. Notice how we have just defined two relationships. The cost depends on the temperature, and the temperature depends on the day. Using descriptive variables, we can notate these two functions. The function c of t gives the cost c of heating a house for a given average daily temperature in T degrees Celsius. The function t of d gives the average daily temperature on day d of the year. For any given day, cost equals c of t of d means that the cost depends on the temperature, which in turn depends on the day of the year. Thus, we can evaluate the cost function at the temperature, t of d. For example, we could evaluate t of 5 to determine the average daily temperature on the 5th day of the year. Then, we could evaluate the cost function at that temperature. We would write c of t of 5. Cost for the temperature equals c of t of 5. Temperature on day 5 equals t of 5. By combining these two relationships into one function, we have performed function composition, which is the focus of this section. 1.4.1. Combining functions using algebraic operations. Function composition is only one way to combine existing functions. Another way is to carry out the usual algebraic operations on functions, such as addition, subtraction, multiplication and division. We do this by performing the operations with the function outputs, defining the result as the output of our new function. Suppose we need to add two columns of numbers that represent a husband and wife's separate annual incomes over a period of years, with the result being their total household income. We want to do this for every year, adding only that year's incomes, and then collecting all the data in a new column. If W of Y is the wife's income and H of Y is the husband's income in year Y, and we want T to represent the total income, then we can define a new function. T of Y equals H of Y plus W of Y. If this holds true for every year, then we can focus on the relation between the functions without reference to a year and write T equals H plus W. Just as for this sum of two functions, we can define difference, product, and ratio functions for any pair of functions that have the same kinds of inputs, not necessarily numbers, and also the same kinds of outputs, which do have to be numbers, so that the usual operations of algebra can apply to them, and which also must have the same units, or no units, when we add and subtract. In this way, we can think of adding, subtracting, multiplying, and dividing functions. For two functions f of x and g of x, with real number outputs, we define new functions f plus g, f minus g, f, g, and f over g by the relations open parenthesis, f plus g, closed parenthesis, of x equals f of x plus g of x, open parenthesis, f minus g, closed parenthesis, of x equals f of x minus g of x, open parenthesis, f multiplied by g, closed parenthesis, of x equals f of x dot g of x, open parenthesis, f divided by g, closed parenthesis, of x equals f of x over g of x. Example 1. Performing algebraic operations on functions. Find and simplify the functions. Open parenthesis, g, minus f, closed parenthesis, of x, and, open parenthesis, g, over, f, closed parenthesis, of x, given f of x, equals, x, minus 1, and, g of x, equals, x squared, minus 1. Are they the same function? Solution. Begin by writing the general form, and then substitute the given functions. Open parenthesis, g, minus f, closed parenthesis, of x, equals, g of x, minus f of x. Open parenthesis, g, minus f, closed parenthesis, of x, equals, x squared, minus 1, minus, open parenthesis, x, minus 1, closed parenthesis. Open parenthesis, g, minus f, closed parenthesis, of x, equals, x squared, minus x. Open parenthesis, g, minus f, closed parenthesis, of x, equals, x, open parenthesis, x, minus 1, closed parenthesis. Open parenthesis, g, over, f, closed parenthesis, of x, equals, g of x, over, f of x. Open parenthesis, g, over, f, closed parenthesis, of x, equals, x squared, minus 1, divided by, x, minus 1, where x is not equal to 1. Open parenthesis, g, over, f, closed parenthesis, of x, equals, open parenthesis, x, plus 1, closed parenthesis, multiplied by, open parenthesis, x, minus 1, closed parenthesis, divided by, x, minus 1, where x is not equal to 1. Open parenthesis, g, over, f, closed parenthesis, of x, equals, x, plus 1, where x is not equal to 1. No, the functions are not the same. Note. For, open parenthesis, g, over, f, closed parenthesis, of x, the condition x is not equal to 1 is necessary because when x equals 1, the denominator is equal to 0, which makes the function undefined. Try it number 1. Find and simplify the functions, open parenthesis, fg, of x, and, open parenthesis, f, minus g, closed parenthesis, of x. F of x, equals, x, minus 1, and, g of x, equals, x squared, minus 1. Are they the same function? 1.4.2. Create a function by composition of functions. Performing algebraic operations on functions combines them into a new function, but we can also create functions by composing functions. When we wanted to compute a heating cost from a day of the year, we created a new function that takes a day as input and yields a cost as output. The process of combining functions so that the output of one function becomes the input of another is known as a composition of functions. The resulting function is known as a composite function. We represent this combination by the following notation. Open parenthesis, f, ring operator, g, closed parenthesis, of x, equals, f of g of x. We read the left-hand side as f composed with g at x, and the right-hand side as f of g of x. The two sides of the equation have the same mathematical meaning and are equal. The open circle symbol, ring, is called the composition operator. We use this operator mainly when we wish to emphasize the relationship between the functions themselves without referring to any particular input value. Composition is a binary operation that takes two functions and forms a new function, much as addition or multiplication takes two numbers and gives a new number. However, it is important not to confuse function composition with multiplication because, as we learned above, in most cases, f of g of x is not equal to f of x multiplied by g of x. It is also important to understand the order of operations in evaluating a composite function. We follow the usual convention with parentheses by starting with the innermost parentheses first and then working to the outside. In the equation above, the function g takes the input x first and yields an output g of x. Then the function f takes g of x as an input and yields an output f of g of x. G of x, the output of g is the input of f. F composed with g at x, equals, f of g of x. X is the input of g. In general, f composed with g, and g composed with f, are different functions. In other words, in many cases, f of g of x is not equal to g of f of x, for all x. We will also see that sometimes two functions can be composed only in one specific order. For example, if f of x equals x squared and g of x equals x plus 2, then f of g of x equals f of x plus 2 equals open parenthesis x plus 2 closed parenthesis all squared equals x squared plus 4x plus 4. But g of f of x equals g of x squared equals x squared plus 2. These expressions are not equal for all values of x, so the two functions are not equal. It is irrelevant that the expressions happen to be equal for the single input value, x equals -1 over 2. Note that the range of the inside function, the first function to be evaluated, needs to be within the domain of the outside function. Less formally, the composition has to make sense in terms of inputs and outputs. A. Composition of functions. When the output of one function is used as the input of another, we call the entire operation a composition of functions. For any input x, and functions f and g, this action defines a composite function, which we write as f ring g, such that f composed with g at x equals f of g of x. The domain of the composite function, f composed with g, is all x, such that x is in the domain of g, and g of x is in the domain of f. It is important to realize that the product of functions fg is not the same as the function composition, f of g of x, because, in general, f of x, multiplied by g of x, is not equal to f of g of x. Example 2. Determining whether composition of functions is commutative. Using the functions provided, find f of g of x and g of f of x. Determine whether the composition of the functions is commutative. F of x equals 2x plus 1. G of x equals 3 minus x. Solution. Let's begin by substituting g of x into f of x. F of g of x equals 2 times, open parenthesis, 3 minus x, closed parenthesis, plus 1, equals 6 minus 2x plus 1 equals 7 minus 2x. Now we can substitute f of x into g of x. G of f of x equals 3 minus, open parenthesis, 2x plus 1, closed parenthesis, equals 3 minus 2x minus 1 equals negative 2x plus 2. We find that g of f of x is not equal to f of g of x, so the operation of function composition is not commutative. Example 3. Interpreting composite functions. The function c of s gives the number of calories burned completing s sit-ups, and s of t gives the number of sit-ups a person can complete in t minutes. Interpret c of s of 3. Solution. The inside expression in the composition is s of 3. Because the input to the s function is time, t equals 3 represents 3 minutes, and s of 3 is the number of sit-ups completed in 3 minutes. Using s of 3 as the input to the function c of s gives us the number of calories burned during the number of sit-ups that can be completed in 3 minutes, or simply the number of calories burned in 3 minutes, by doing sit-ups. Example 4. Investigating the order of function composition. Suppose f of x gives miles that can be driven in x hours, and g of y gives the gallons of gas used in driving y miles. Which of these expressions is meaningful? F of g of y, or g of f of x? Solution. The function y equals f of x is a function whose output is the number of miles driven corresponding to the number of hours driven. Number of miles equals f of number of hours. The function g of y is a function whose output is the number of gallons used corresponding to the number of miles driven. This means number of gallons equals g of number of miles. The expression g of y takes miles as the input and a number of gallons as the output. The function f of x requires a number of hours as the input. Trying to input a number of gallons does not make sense. The expression f of g of y is meaningless. The expression f of x takes hours as input and a number of miles driven as the output. The function g of y requires a number of miles as the input. Using f of x, miles driven, as an input value for g of y, where gallons of gas depends on miles driven, does make sense. The expression g of f of x makes sense, and will yield the number of gallons of gas used, g, driving a certain number of miles, f of x, in x hours. Q&A. Are there any situations where f of g of y and g of f of x would both be meaningful or useful expressions? Yes. For many pure mathematical functions, both compositions make sense, even though they usually produce different new functions. In real-world problems, functions whose inputs and outputs have the same units also may give compositions that are meaningful in either order. Try it number 2. The gravitational force on a planet a distance r from the Sun is given by the function g of r. The acceleration of a planet subjected to any force, F, is given by the function a of F. Form a meaningful composition of these two functions, and explain what it means.